Hello friends, this video on Thermodynamics part 7 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure that you have watched part 1 to part 6. Having understood the basic concepts of chemistry, for example, the intensive extensive process, the path state function, the path functions, and the reversible irreversible process, let's introduce internal energy. What is internal energy? Internal energy of a system is nothing but the total energy contained by a thermodynamic system. It can be chemical energy, electrical energy, mechanical energy, rotational energy, vibrational energy, potential energy, nuclear energy, any energy you can think of. System will have a lot of energy, right? Mechanical, chemical, electrical, rotational, vibrational, potential, nuclear. You add all the energy possible. The total energy is the internal energy. But how will you determine? There's so many energies in the system. How will you determine? For example, I have one glass of water. It will have so many energy. It will vibrate. If you rotate with something rotational, it will have mechanical energy, it will have some chemical energy, potential energy. How will you calculate? It is impossible to calculate internal energy of the system. Now the question is, if you can't calculate internal energy of the system, why are we studying this? Doesn't make sense, right? If you can't calculate something, why will you study? Just tell it's out of science school. But wait, we care only about change in internal energy. We care only about delta U, that is change in internal energy. Internal energy is denoted by U, but we care only about delta U because U is something which is very difficult, almost impossible to determine. So we don't care about U. We care about delta U, and that is something which we can find. That is something which you can derive from experiments and using some mathematics. So we care about delta U, change in internal energy, and that is something which we can find. So how can we see a change in internal energy of the system? So internal energy change we can see when work is done on a system. For example, I have this pressure, volume, temperature, gas here. You put some mass, you put some more mass. There's a work done on this, right? With this, there will be some change in internal energy of this system, and we can derive that. We can find. Internal energy change is also done when we pass some heat. For example, you have this wood, you burn this. Assuming it is not adiabatic, the wall is not adiabatic, and you can just pass the heat. For example, in this case, the heat flow happens. There's a test tube, you heat it. You pass the heat to the system, and there is a change in internal energy. You see, you put a glass of water or a bowl of water in the microwave, it burns, it boils. In the gas stove, it boils because you pass the heat to the system. The internal energy change can also happen when the mass enters or leaves the system. For example, as I told, you have this big beaker and it has some water, it has some internal energy. You divide you take out some water, obviously the internal energy will change, right? We can have the internal energy change using that way also, right? So there are the various ways where we see the internal energy change for a system, but we'll be focusing more on the first two, where the work is done on the system or by the system, or the heat is passed into the system or out of the system. Maybe the system is emitting heat. For example, you have a cup of coffee, hot coffee. You print right properly. You have this cup of hot coffee. You keep it. It becomes cold. Why? Because the system is a system now. It transfers heat to the surrounding. You have a bowl, and you supply heat to this. It becomes hot. Why? Because we are giving heat to the system. Similarly, in this case, the work can be done by a system or work done on the system. So we'll be focusing more on those two parts where we talk about the change in internal energy by the work done on the heat. And there are some features of the internal energy. So before we even understand this internal energy or change in internal energy deeper, let's understand some of the features so that it's easier for us to understand this, right? So if we know someone, it's the name, the property of someone, it's more easy to become friends. For example, if I want to make some person in my class as my friend, it's good to know his name, his likes, dislikes, so that we can build a friendship. Same thing, if you want to understand this, you want to build a relation with the internal energy, it's good to understand the feature of the internal energy. So if you see, the first feature is extensive property. That means it depends on the quantity of substance. For example, if the whole system has internal energy E, big E, if I divide this with some Planck, this will have E by 2 and this will have E by 2, assuming the volumes are same. So it depends, it is extensive property. The internal energy is extensive property. And internal, when you talk about the internal energy, you talk about heat evolve or absorb at constant volume. Please note, it's very, very critical. That's why I put this blue and dark, bold. When we talk about internal energy change, we talk about internal energy change at constant volume only. Because if the volume is not constant, we'll see that there's some work done by the system. They expand, there's some work done. We don't want to take all this headache now, because we're just understanding the internal is very basic. So we'll keep the volume constant. So when you talk about internal energy, now since we are starting, we'll talk about internal energy change only when the volume is constant. Constant volume, that means we're talking about internal energy. If you are saying that I have a beaker here, a test tube here, I'm doing some reaction, can I talk about internal energy change if this is open? No. Big? No. You talk about internal energy change only when the volume is constant. I'm repeating it. The internal energy change, we talk about it only when the volume is constant. If the volume is not constant, we'll not talk about internal energy change. We'll talk about something else which we'll discuss later. But now, when you talk about internal energy change, we talk about constant volume. Right? Now we have some sign convention, because as I told, if I have the system may give energy or may take energy, right? Because the energy may increase, may decrease. So the system is giving energy. I say delta U is negative, that the system has become poorer. So it is negative because the system has lost the energy. So delta U is negative. The system has gained the energy, system has become richer. If system is richer, delta U is positive. Hope you understand this. Let me repeat this. This is a critical sign convention we follow. This is a sign convention. Somebody will ask why it is not other way around. Thus the chemist has thought this is the best way. Let's keep following it. If the system absorbs, just do one thing. As a viewer, just view things. This is my eye actually. This is a guy, this is a big guy. From system perspective. Don't think about surrounding. Think from system perspective. When we told surrounding is something we don't care. Surrounding may be considered the whole room. Surrounding may be considered the whole universe, whole earth. So this is something which is not concrete. System is concrete. System is concrete. So think from system perspective. If system is gaining energy, delta U is positive. System is becoming richer. If system is losing energy, delta U is negative. That is, system is becoming poorer. Right? So think from system perspective. Always you will not have issue with the sign convention. Because we have two choices, system or surrounding. Surrounding is not sure. We don't know what is surrounding. System is concrete. So think from system perspective. System gets some energy. System gets some energy. It is positive. System, it's more and more energy. The system loses some energy. That means system is becoming poor. Delta U is negative. Correct? For isothermal process, delta U is 0. Why? Isothermal process means temperature is constant. And since we are talking about change in internal energy, I am saying volume is constant. Correct? See, When the moment you talk about internal energy, the volume is constant, temperature is constant. Temperature, volume is constant. We have this gas law, PV is equal to nRT. So N is constant, R is constant, T is constant, V is constant. Pressure will also be constant. Everything is constant. Delta U is, there's no change in that. Everything is same, right? So for isothermal process, there is no change in internal energy. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.